What if I told you there's a way to find every single occurrence of a pattern inside a massive text, not just fast, but in guaranteed linear time, like no matter how tricky the input is? Well, today, we're unpacking one of the most elegant solutions in string processing, the Z algorithm. So let's get into how it actually works under the hood. We've all used Command F to find a word in a document. It feels instantaneous, right? But how does a computer actually pull that off so efficiently, especially when it's scanning millions of characters? The brute force way is just way too slow. There's a much, much smarter approach.
And the secret weapon here is a really clever pre-processing step. Before we even think about searching, we analyze our string and build this special map. You can think of it like a cheat sheet. It's called the Z-array. And honestly, it's the key that unlocks this incredible speed.
Okay, so what in the world is the Z-array? Let's just forget the complex theory for a minute and build one together step by step. It's actually pretty intuitive once you see it in action.
So here's the core idea, and it's simpler than it sounds. Imagine you're standing at every single character in your string, one by one. The Z-array just answers one question for each spot. Starting from right here, how many characters match the very beginning of the whole string? That's it. It's like a little map that flags every single spot that kind of looks like the start.
The best way to really get this is with an example. So we're going to build the Z-array for this nice little palindrome, ABCA, BA.
First things first, there's a little special rule, a bit of a convention. The value at index 0, Z of 0, is kind of an odd case. The substring starting at index 0 times is the whole string. So, by convention, we just set its value to the total length. In this case, that's 7. Easy enough. All right, now for the real work. Let's look at index 1. The substring starting here is baka ba. Our string's prefix, the very beginning, starts with A. Does B match A? Nope, not at all. So the Z value is 0. Simple. Same thing happens at index 3. The substring is kaba. Does C match our prefix A? Again, nope. So Z3 is also 0. But then we get to index 4, and this is where it gets interesting. The substring here is ABA. Now, does that match the prefix of our original string abba kababa? Yes, it's a perfect match. ABA. That's 3 characters long, so we put a 3 in our Z-array at index 4. See how that works? And if we just keep doing this for every single position, we get our final Z-array. Don't be fooled by how simple it looks. It's just an array of numbers, but it actually encodes a huge amount of structural information about our original string. Okay, so doing that by hand was fine for, 7 characters. But if we did it that way on a computer, checking every position from scratch, it would be painfully slow on large files. So how do we get this done in lightning-fast linear time? Well, this is where the real genius of the algorithm comes in. Right, that naive approach would mean nested loops, which lands us with that dreaded O of n squared complexity. We can do so much better by just being smart and not redoing work we've already done. The absolute key to this is something we'll call a Z-box. Just think of it as a sliding window. It has a left and right boundary, L and R, and this box always covers the rightmost chunk of the string that we've already confirmed is an exact copy of the prefix. So here's the trick. As we're scanning along the string to compute our Z values, if our current position I happens to fall inside that Z box, we get a major shortcut. We already know this section is a copy of the prefix, and that means the Z value we need for this spot is directly related to a Z value we've already calculated, way back in the beginning. We can reuse that previous value to either fill in the answer instantly or at least get a massive head start. We only have to start comparing character by character if we think we can extend a match beyond our current Z box. And if we do, we just slide the box forward. And this is the whole point of the Z box, because that right boundary of the box, R, only ever moves forward. It never backtracks. This simple fact guarantees that we never get stuck recomparing the same characters over and over. Each character in the string is only ever looked at a handful of times, at most. And that is the simple idea that slashes the complexity from quadratic all the way down to linear. And the difference here is just it's night and day. We go from a sluggish, quadratic slowdown that becomes totally unusable on large texts to this incredibly sleek linear time algorithm that scales beautifully. It's a real game changer. So we have this awesome tool for analyzing a single string, but the original question was, how do we use it to find a different string,
our pattern, inside a big block of text.
The trick here is just wonderfully elegant. Instead of trying to analyze two separate strings, we cleverly merge them into one single purpose-built string that we can just feed right into our Z algorithm.
So let's say we want to find the pattern ABA inside the text ABABAB.
Okay, so what we do is we concatenate them, but we stick a special separator character in between. And this is important. It has to be a character that doesn't appear anywhere in our pattern or our text. So we end up with this new string, our pattern, then our special character, then our text.
And now we just build the Z-array for this new combined string. And think about it for a second. The prefix of this new string is our pattern, right? So anywhere later in the string, in the part that was our original text, that we find a Z-value exactly equal to the length of our pattern, well, what does that mean? It means the substring starting right there is a perfect match for our pattern. It's a crystal clear signal. That's it.
Now look, the Z algorithm is fantastic, but it's not the only player in the game. To really appreciate it, it helps to see how it stacks up against some of the other heavy hitters in string matching.
So you've got the famous KMP algorithm. It also runs in linear time, but its core logic is based on analyzing the borders of prefixes, which is a slightly different way of thinking about the problem. Then there's Robin Karp, which uses hashing. It's usually linear time, but can, in some rare worst-case scenarios, slow down. The Z algorithm's logic is, you could argue, one of the most direct and intuitive. It just measures how much the string matches its own prefix, starting from every possible position. So let's just tie this all together. What are the big takeaways? First, at the heart of everything is the Z-array, that simple but powerful map of prefix matches. Second, the sliding Z-box is the crucial optimization that lets us build that array in super fast linear time by not redoing work. And finally, that pattern plus separator plus text trick lets us use this whole mechanism to make pattern matching incredibly simple and fast.
We've seen how this works beautifully with simple ASCII characters. But this leaves us with a final thought. In the real world, text is messy, right? It's filled with complex Unicode, emojis, all sorts of different character encodings. So how does an algorithm that's built on these simple character-by-character comparisons adapt to handle that kind of real-world complexity? That's something to think about.